This video is on pressure and the effects that pressure has on boiling and freezing points. So we're starting here talking about gases, and gases in their constant random motion will strike the walls of any container that they're put in. And this is the visual that I want you to have when you think about gas pressure, just gas particles banging on the walls of a container, and that'll serve you well. So when we talk about energy and boiling, when we think about a boiling point, if you've ever had to define it, most people kind of struggle with it and say, well, it's when it starts to form the bubbles. If you look at the legal Schmeigel definition for the boiling point, that's the temperature at which the equilibrium vapor pressure of a liquid equals the atmospheric pressure. So by reading that definition, boiling actually has more to do with pressure than it does with temperature. It is dependent on the atmospheric pressure and how that compares to the vapor pressure of that particular liquid. So pressure greatly affects the boiling point of a liquid. Now, when we talk about a normal boiling point, we're talking about what we would normally experience. So up until you've had this class, if I ask you the boiling point of water, you'd say 100 degrees C. That's just when water boils. That is when water boils at the pressure that we're at most of the time. And our standard pressure is 1 atmosphere of pressure, or 760 millimeters of mercury, or 101.3 kilopascals. So when we talk about the boiling point, we have totally been ignoring the pressure, because for most of our day-to-day lives, we live under pretty constant pressure. It fluctuates here or there, but it's really pretty constant. And so our boiling point seems like a constant as well. But if the pressure changes, so does the boiling point. Now, I have a video here, and this is going to show you making cold water boil without adding heat. So what you're going to see in this video is a flask that has some water in it. This flask is hooked up to an evacuation pump, and that's going to pump all the air out, or a lot of the air outside of the flask. And so that's going to lower the pressure inside the flask. And then you're going to start to see that the water will boil. Now, this flask is sitting on a tabletop. It does not have any heat being added to it at all. So let's look at this. So here we have the flask and the tube hooked up to the evacuation pump. It's going to turn on the evacuation pump, and that's going to start pumping air out of the flask. And again, the flask is on a tabletop. And here pretty soon, you're going to start to see little bubbles and then full-on boiling. Now, this water is not hot. You could take it out of there and pour it over your hand, and it would feel like tap water. So we made it boil without adding heat. All we did was manipulate pressure. Now, the lower the atmospheric pressure, the lower the boiling point. So we lowered the pressure a whole lot in that video that you just saw. And so our boiling point was at a much, much lower temperature, just about the temperature in a room. And this works for all kinds of things. If your parents may own an Instapot or a pressure cooker, and those are advantageous because we can add pressure to things and cook at a higher temperature. Because if we add pressure, our boiling point goes up. One of the things that we're going to talk about a little bit later is we'll talk about how when a substance is going through a phase change, its temperature does not change at all. So if I had a pot of water on the stove and it was boiling, it would be 100 degrees C. If I cranked up the heat and added even more energy to it, that water would still measure at 100 degrees C, because the extra heat is going into breaking attractive forces and not going into raising the temperature of the substance. So as long as something's going through a phase change, its temperature is constant. So if we add pressure, we can get water, instead of boiling at 100 degrees C forever, we can get it to boil at a higher temperature, like a 105 or something along those lines, and we can actually cook our food faster, which is why people own an Instapot. It cooks in an instant compared to what it would have taken. Other things that will affect, an added thing to this is elevation. So high elevations have low atmospheric pressure. So the atmosphere that is around us is made up of gases, and we have like this a whole blanket of gases covering the Earth. Well, those gases are in constant random motion, and they're creating this atmospheric pressure. If you are at low elevations, you have a higher column of air up above you, and all of those particles are pushing down on you. So you have greater pressure at lower elevations. If you're at higher elevations, you have less air up above you, so there's less air pressure. Because there's less pressure at high elevations, your boiling point is lower. If we talk about Mount Everest, so the highest mountain above sea level, water will boil at 70 degrees C there instead of 100 degrees C. So if you were cooking on top of Mount Everest, you would have to cook food a whole lot longer to compensate for the lack of heat that you're not getting. It's because the water would boil at 70 degrees C, which you could put your hand in and it would feel like a warm little bath. All right. Heat of vaporization. Heat of vaporization is something we'll revisit when we get into thermochemistry, but it's the amount of heat that's needed to vaporize 1 gram of a liquid at its boiling point. So it indicates the strength of the intermolecular forces. For example, the heat of vaporization of water is 2,260 joules per gram. A gram of water is a milliliter of water. So a tiny, tiny little bit of water takes 2,260 joules of heat. That's an enormous amount of heat just to heat up a milliliter of water. And the reason that water has such a high heat of vaporization is because water has really strong intermolecular forces, and it takes a lot of heat to break strong intermolecular forces, those hydrogen bonds. Freezing and melting. The freezing point is the temperature at which the solid and liquid are at equilibrium. So when we hit 32 degrees Fahrenheit and we start thinking about, oh, maybe things will freeze. Yeah, they will at 32 degrees Fahrenheit. They also melt at 32 degrees Fahrenheit. So you've got your freezing and melting happening at the same rate. It just matters on what happens next. The normal freezing point, again, if we talk about normal, we're keeping our pressure at standard pressure or 1 atmosphere of pressure. Freezing and melting happen at the exact same temperature. Like I said, it just matters where you go after that. Now, just like we had heat of vaporization, we also have heat of fusion, and this is the energy required to melt 1 gram of a solid at its melting point. And again, it depends on those intermolecular forces, because to go from a solid to a liquid, you have to break some of those attractive forces, and heat of fusion is an indication of that. So the heat of fusion, again, for water, is going to be 334 joules of energy for every gram of ice. And that's quite a bit of heat there. And when you add ice to a drink, what happens, the way your drink ends up being at a lower temperature, is that the heat is absorbed from the drink, is absorbed by the ice, and that heat is used to melt the ice. So your ice doesn't make your drink cold, your drink makes your ice warm and melts it, and that's how it gets rid of the heat.